Welcome to this video on vertical spring mass systems. In this video, I'll be looking at the physics behind the movement of an oscillating mass spring system, looking particularly at forces and energy. First of all, let's consider the following video. Here we have a mass spring system doing nothing at the moment. We're going to let that run in normal speed. We can see that under free fall, this mass oscillates up and back. We've set this up with zero dampening, so this will oscillate continually without losing any energy from friction. Let's add in, first of all, the natural length of the spring. So when the spring is resting, this is its natural length. We're going to put in the equilibrium or midpoint, so that's in the center here. So if we slow this down, we can see what we have is a spring as it comes right back up to the top, goes through the equilibrium, it hits the top. Okay, at this point, there is no extension in the spring whatsoever. Gravity is going to pull this down, and it starts to move. We hit the middle point, okay? It continues on, gets to the bottom, stops for a second, and then it moves back up. And that's pretty much why we call it an oscillation. It's completely cyclical, and it repeats over and over again. Let's now look at some of the vectors involved with this particular motion. Okay, we'll get this moving nice and slowly. First of all, let's consider gravity. Now, gravity is shown by this red arrow here. Gravity does not change. It's the same magnitude and the same direction always. In fact, it's 9.8 newtons per kilogram towards the center of the Earth. Nothing surprising there. Let's consider the spring force. Now, the spring force is in the opposite opposing direction to gravity, and its magnitude continually changes. So at the top, we can see the spring is not extended at all, and so it operates and generates with no force. So at this point, all we have is a weight force due to gravity pulling down. Now, as the spring begins to stretch, it generates a force pushing back up opposing gravity. So it's starting to build a force. In the center point, you see that the gravitational force or the weight force due to gravity is equal and opposite to the spring force pushing back up because the spring is being stretched. Now, if we let this continue, you'll see that the spring is fully stretched just before it returns back up, and there's a maximum force on the spring trying to restore that back to its original length. So let's now have a look at the net force as this continues to oscillate. So at the top, the net force is fully being generated by the gravity. Okay, if we keep continuing. In the middle, we find the net force is zero, and that's because the spring force going up and the gravitational force going down are equal. Continue to rotate. We find down the bottom, the net force is back upwards. And that's because the spring force is considerably larger in magnitude and opposite in direction to the gravitational force. So hopefully that makes sense in terms of why our net force changes. What you will notice is anywhere in the system, the net force is always towards this equilibrium position. In the bottom half, it's operating upwards towards the equilibrium middle position. In the top half, it's operating downwards towards the equilibrium system in the middle. Okay, a couple of other vectors to consider. Let's look at, first of all, the acceleration. No surprises here. The acceleration should always follow the net force. So when the net force is pushing up, the object will accelerate upwards. Newton's second law, F equals ma. When the net force on the system is pushing downwards, the acceleration will be downwards. Have a look at the magnitude. At the bottom here, there's quite a large magnitude, it's represented by the size of this arrow, a large acceleration towards the center of the system, towards the equilibrium point. In the middle, just missed it, you can see there's zero acceleration right in the center. Now, towards the top, there is acceleration and the force is acting towards the equilibrium position in the middle. Okay, so when we consider this at the start, there's a great strong force towards the center and there is acceleration towards the center, quite a large acceleration. Once we start moving, however, the spring stretches and that force and acceleration is reduced to the point where it's zero in the middle. Then what we find is that the spring force is greater than the gravitational force from here onwards. And so the net force and also the acceleration is back towards the center of the equilibrium system. So again, we have zero acceleration in the middle, maximum towards the center at the top, zero in the middle, maximum towards the center at the top. Finally, let's see what that does to the velocity. We find at the top, the turning point, we've got zero velocity, gets bigger and bigger. It's at its fastest velocity right in the middle when the acceleration is zero. And that's because it's been accelerating all the way down to this point. This is its maximum velocity. Once we go past the equilibrium point, we find the spring is pulling it back towards the center, and the spring force is greater than the gravitational force. And so we find that it decelerates. Velocity reaches 0, then turns and directs itself back towards equilibrium. Fastest in the center, nothing at the top. So to summarize, the velocity at the top is 0, the velocity in the middle is maximum at the equilibrium, and the velocity at the bottom is 0. Let's now step through these processes. We know that during this oscillation, there's always a force due to gravity that's constant, pushing towards the center of the Earth, downwards in this case. There is also a second force, the force due to the spring, that must be considered, and that varies throughout the oscillation. So at the top, when the spring is unstretched and it's being held, supported by this hand, we have a downwards force in green, force due to gravity, which is equal to mg, and at this point, we have no spring force. So the net force is the gravitational force minus the spring force. So gravitational force minus 0 means the net force is just the force due to gravity, mg. Now let's consider what happens when we get to the midpoint or the equilibrium point of this oscillation. Again, we still have our force due to gravity, Fg, but now as the spring's being stretched, we have a force due to the spring pushing back up. So at the midpoint where there's an equilibrium position, we have the force due to gravity, mg, pulling down is equal and oppositely opposed by the force due to the spring, kx, pushing back up. So at this point, the two forces cancel each other out and there is a net force of 0. So we can say that the force due to gravity, mg, will be equal to the magnitude of the force due to the spring, kx. So at this equilibrium position, the two forces are equal and opposite, and the net force is considered to be 0. Finally, at the third and final position, the bottom position of this oscillation, fully stretched, we still have both forces operating. We have a force due to gravity pushing down, but we have a very, very large force due to the spring pushing back up. This is because the spring has now been stretched considerably. It's greater in magnitude, and so when compared to the force due to gravity, it is greater, okay, and it will generate an upwards force back towards the equilibrium position. So at this point, we have a gravitational force of mg, we have a spring force of kx. The net force, we consider the larger force to be heading in the direction of the net force. So the net force is the spring force minus the gravitational force, or kx take mg. Let's now consider a summary of these findings. So at the top, we know the net force is equal to mg when the spring is unstretched. At the middle, or the equilibrium position, we know the two forces are equal. Fg equals Fs. The force of gravity equals the force of the spring. So mg equals kx. And finally at the bottom, when it's fully stretched, we know that the net force is kx take mg. The net force, and therefore the acceleration, always acts towards the midpoint or the equilibrium point through the oscillation. So at the top, net force is operating downwards. At the midpoint or the equilibrium position, the net force is 0. They cancel out. And when I say they, I mean the spring force and the gravitational force. And at the bottom, the net force is pushing back towards the equilibrium position. So remember, no matter where the mass is in the system, it is always being forced towards the equilibrium or midpoint. Let's now have a look at the acceleration and speed. So we know the net force, and therefore the acceleration, always acts towards the midpoint or the equilibrium point. How does that affect the speed? So at the top, we find we have a net force operating towards the equilibrium position, which means our acceleration will also be in the same direction, according to Newton's second law, F equals ma. But at this point, just before it falls, we have a speed of 0. So at the top unstretched, we have a net force downwards, acceleration downwards, but an instantaneous speed of 0. Let's now consider in the center at the equilibrium position. At this point, we have a net force of 0, which means we have an acceleration of 0, according to Newton's second law, F equals ma. At this point, however, the system has been accelerating all the way down to this point, so it's reached its maximum speed. We continue on now to the bottom of our oscillation. At this point, the net force is being operated back towards the equilibrium position. It therefore has an acceleration in the same direction back up. And again, much like at the top, we have this time a velocity of 0 at the bottom at that instance before it accelerates back towards the equilibrium position. Let's now return to our PhET simulator to examine further aspects of this oscillating vertical mass spring system. So we were looking at the vector nature when we last looked at the PhET simulator. Let's now move across to the energy consideration. So we have our spring all set up mass of 100 grams about to drop from a rested position or an unstretched position. So it's going to drop and it will fall through the equilibrium right down to the bottom and then return back again through the equilibrium back up to the top. Now, if you're observant, you would have noticed the graph information on the left-hand side here. In an unstretched position, we have a total gravitational potential energy because we have a mass elevated some height from a reference position. So at this point, the total energy of our system is completely gravitational potential energy. Now it's worth noting, if it was me doing this simulation and calculation, I would, if possible, move my height to the point where the mass oscillates to the lowest position. I wouldn't reference it below that. It makes the calculation simpler when you get to problem solving. But one of the limitations with this simulator is that I can't move this height to the position where the mass stops at the bottom. So there's always in this scenario going to be some level of gravitational potential energy, unfortunately. Let's run through this. As it falls, we find that the spring stretches, and so there's a gain in what we have here, elastic potential energy, what I call strain potential energy. You'll also notice that the object's now moving, and so there's also kinetic energy. Now, where did that come from? You'll see that the gravitational potential energy has been reduced considerably. In fact, it's about half what it was originally at the top, which makes sense because it's now got only half the delta H to fall through. So we have lost gravitational potential energy, but in turn we've gained kinetic energy through movement and velocity, and we've gained strain potential energy in the spring as it stretches. Let's continue on. We eventually hit the bottom point. Now at this bottom point, if we reference the height as 0 here, we would have absolutely no gravitational potential energy. Here, we've reached the speed of 0, so the kinetic energy has reached 0. However, we have a large amount of strain potential energy stored in the spring, and that can be seen by the large light blue section here in the graph. So let's let this run. You'll see we're continually increasing our kinetic energy, then decreasing our kinetic energy, then increasing our kinetic energy. It's not a vector because it uses speed, not velocity. So it gets to a maximum at the equilibrium position, then drops to 0 at the top at the unstretched. A maximum at the equilibrium, and then drops to 0 at the bottom of the oscillation. The gravitational potential, as it elevates higher, it gets a larger gravitational potential, and as it falls, reducing the delta H, we get a lower gravitational potential. In terms of elastic energy, we find when the spring's at the top of the oscillation, there's no strain potential energy. When it gets to the bottom, it is a maximum strain potential energy. There is no friction in this system. It's an ideal spring system, so there's no thermal energy being wasted. Which means when we add these together anywhere in the system, the total amount of energy remains constant. It's only the forms that change from complete gravitational potential to an increase in kinetic and strain potential. Finally, let's consider the energy changes within this spring mass system. So we have three forms of energy to consider. We have the gravitational potential energy, which exists for any object that has mass and elevated at a height within a gravitational field strength. We also have a second form, kinetic energy, which exists for any object with a mass that has speed. And finally, strain potential energy that occurs within the spring, and it's the product of half the spring constant, K, times the extension delta x squared. Of course, also, I forgot to mention, our reference height is very important. We need to choose a reference position from which to calculate our gravitational potential energy. And for these type of problems, it's the easiest and most convenient to choose the reference height at the lowest point in the oscillating system. So, a reminder that anywhere in the system at any time, no matter where the mass in the spring, the sum of the energy, the total energy, is going to be the sum of the gravitational potential and the kinetic and the strain potential. So at the top, when it's unstretched, we have definitely a gravitational potential, mgh. Because the speed is 0, there is no kinetic energy, and because there's no extension, there's no strain potential energy. So at the top, we find the total amount of energy in the system is just the product of mgh, the gravitational potential energy. Now, if we move it and allow it to stretch to the middle or the equilibrium position, we still have three forms of energy, and the total energy of the system is the sum of each. So at the midpoint, the equilibrium position, we have still a gravitational potential energy, mgh. Notice this is a different h. It's now only half of what it was originally. So accordingly, there'll only be half the gravitational potential energy. However, we now have an object that's moving with mass, so we do have kinetic energy, and the spring has been stretched a distance, delta x, as can be seen on your screens. So we also have a strain potential energy. So at this midpoint, the actual statement for the sum of all energy is mgh plus a half mv squared plus a half k delta x squared. It's the sum of the gravitational potential, the kinetic, and the strain potential. All three forms are present at this position in our oscillating system. Finally, at our third and final position, we have at the bottom, where the spring is being fully stretched, we have at this point h of 0. We've reached our reference point, so there's no gravitational potential energy. The objects have stopped moving at this instance, and so the speed is 0, so we have no kinetic energy. The spring has been fully stretched at its maximum distance, delta x. Okay, so at this point, we do in fact have a large deal of elastic strain potential. So at the bottom, when it's fully stretched, we find the total energy in the system is purely being produced by the strain potential energy of the spring, a half k delta x squared. As a summary, at the top, the total energy of the system is gravitational potential, mgh. At the midpoint, all three forms of energy are present, and you have to add all three together to work out the total energy. And finally, at the bottom of the system, all the energy is in the form of elastic strain potential. Now please note that at the top, at the midpoint, and at the bottom, these total energies are all equal, which means I could equate the top energy to the bottom energy. I could equate the top to the middle or the middle to the bottom. This allows me to make all sorts of calculations, from the height of the system to the speed of the system, to the spring constant of the system, to the delta x, the extension of the system. So, thank you for watching this video on our vertical mass spring system. I hope it's clarified some of your understandings and given you a better grasp of the physics involved. As always, if you enjoyed this video, please like, please comment, please share. And it'd be great if you could subscribe. As always, thanks for watching.